Okay, so good morning to everyone. So today we will discuss about the topic of heap sort. So heap, then we will work on the heap sort, heapify priority queues. So before starting through the heap sort, we will cover the topics that will be the array representation of the binary tree. So first we will the topics will be covered of the array representation of a binary tree. Then we will discuss about the complete binary tree, and after that we will move into the heap, and after that we will for heap sort, then heapify, and after that we will discuss about the priority queue. So first the topic we will discuss the topics, that is array representation. This is the array representation of a binary tree. So for the array representation of a binary tree, you see a binary tree will be given. You see binary tree are given. That is, in this A, B, C, then D. For B, there is left child D, and for B, there is right child E present. For same as that, for C, the left child is F and the right child is G present. So if we represent this binary tree into the array, if we represent this binary tree into the array, then it will be look like this. Now in this array, you see what we have done in this array by level. We can say by level, we store the nodes. So first A node is stored, then B node is stored, and after that C node is stored, then D, then E, after that F and G. So we can say by level we store the nodes here. In this array we store the nodes by level. So first A is stored. Now here we are starting from index 1. It can be 0 also, but we have started from index 1 here. So here we are starting it from index 1, and in this index 1, first is A node is stored, then in the next index B is stored, third index this C is stored, then fourth index this D is stored, then fifth index this E is stored, and sixth index F, and seventh index G. So by level we store the data, or can say we store the nodes in the array. But now the array, in this array the data can be stored by using the formula also. So what is the formula? The formula, what will be the formula? So the formula is that if a node is at index I, if a node is at index I, then its left child will be present at 2 into I, and its right child will be present in 2 into I plus 1, and its parent will be present at I by 2. So let's take an example and see that it is correct or not. So let's say we have taken B. So we are taking B node here. So the B node is present in which index? Second index. So let's say if a node is present at second index, then its left child will be is at 2 into I. So that means I value is 2. So 2 into 2, 4. That means in 2, B node is present. And in 4, what node is present? D node is present. Okay. Yes, the left child of B is D. You see the left child of B is D. And its right child will be present at 2 into I plus 1. That means 2 into 2 plus 1. That means 5. So in 5, which node is present? In 5, E node is present. In 5, E node is present. And it will be the right child. It will be the right child. Yes, E is the right child of the B. and the parent of b will be what? If we press I, that means I will be 2, so 2 by 2, that means 1. Yes, b's parent is a, b's parent is a. So if we use this formula also, if this formula also, we can fill this array. Using this formula we can fill this array. But this formula, if the length of the our binary tree becomes large, then it is not possible that every time we see the formula and put it into the array. It is not possible, and it becomes hectic also. So what in that case, what we will do, we will see level by level. The nodes we will store in the array will be level by level. But if it is in the small case, let's say in the small length of the array, or we can say the small length of the binary tree, then using the formula, this value can be stored. But I want to show you that the level by level formula, level by level, and using the formula, both are same. That in both way you can store the nodes into the array. So this is the array representation of a binary tree. So we have first see that the array representation of a binary tree. Now another type it is given. You see another type it is given here A, and A's left child is B and right child is C, and B's left child is D and right child is. So if we represent in an array, that means A, after that B and C, and after that D and E. Okay, so no problem, it can be done. Now for here also, it is A, its left child is B, but B doesn't have any child. Further, it's in the C, in this case of C, there is left child D and right child E present. So if we represent it into an array, it will look like A, after that B, BC, after that A, it will be BC, and then here there is no child present, so that's why it uses the gap, and after that D and E. Now, why this gap we use? Instead of here, if we write in this place D and E, let's say we write D and E in this place, and here we place the gap, then you see the formula will not work. Because if, let's say, we are using this, let's say the I value, the formula will be give the wrong result. Because now let's see, in this gap place we use D and E here. So now I value is 2, let's say I value is 2. So after that, what is the left child formula? 2 into I. So 2 into I. Now 2 into I, that means 4. In 4, what we will see in 4, it will present 2 into I, that means in 4, it will be D. But you see, for B, there is no child present. But if we, in this gap, if we didn't give this gap, if we didn't give this gap and place D and E here, then if we check, if we want to check through the our formula, then it will give the wrong result. Because for I equal to 2, that means for B. So here we are taking B's index. So I value will be 2. So I value will be 2. Then the left child formula is what? 2 into I. So 2 into I means 2 into 2. So 2 into 2, that means it will be 4. So here what we have written in the 4, in the array, we have written the 4, in the index 4, D is written. So that means left child of the B will be D. But here you see, it is not the left child of the B, because the B doesn't have any child. Same as that, if we want to check the right child formula, then also 2 into I plus 1, that means 2 into 2 plus 1, it will be 5. So in 5, E is present. Is E is right child of the B? No. So that means this formula, if we didn't give the gap here, If we didn't give the gap in this array, then the formula we will use, it will become wrong. So that's why we have to give this gap. Otherwise, we will see the wrong result. Okay, clear till now? Clear?
Yes, sir.
समझ में?
Yes, sir.
Okay. So this is what our thing. Now the concept is the full binary tree. So for the full binary tree, our total number of elements will be, now if the height of the tree, let's say the height of the tree is h. If the height of the tree is h, then in the full binary tree, the maximum number of nodes, is called the full binary tree. So the total number of elements, will be present 2 to the power h plus 1, 2 to the power h plus 1 minus 1. That means 2 to the power h plus 1 means height of the tree. So here 1, 2, 3. So that means height is 3. So 3 plus 1, height of the tree. So this is what, this will be our 0, 1, 2. So the height of the tree will be, our h will be 2. So here the value will put 2 to the power 2 plus 1 minus 1. That means 2 to the power 3 minus 1. So 8 minus 1, that is 7 elements. So if the height of the tree is 2, that means the maximum number of elements, present will be 7. So if 7 number of elements is present in the height of two trees, then we can say it as the full binary tree. But using this, can we say this is a full binary tree? We cannot say it as a full binary tree, because we have already seen that if the height is true, then the total number of elements present in the tree will be 7. But here we can see only 1, 2, 3, 4, 5. So 2 elements are less. So we cannot call it as the full binary tree. Same as that, here also 0, height will be 0, 1, and 2. So that means total number of elements present will be 2 to the power h plus 1 minus 1. So h will be 2. So 2 to the power 2 plus 1, that will be 3, means 8 minus 1, 7 elements. But here also same, that only 5 elements are present. So we cannot call it as the full binary tree. But if we see in the previous example, we see here, you see 1, 2, 3, 4, 5, 6, 7. So that means we call it as the full binary tree. So full binary tree states that will be the maximum number of nodes. The maximum number of nodes will be, is called the present. If a binary tree, the maximum number of nodes is present, then we call it as the full binary tree. So this we have to, if we want this tree to be the full binary tree, then 2 elements we should have to add in this tree. Similar for in this tree also. If we want this as the full binary tree, then 2 elements should be added. If these 2 elements are added, it will become the full binary tree. Now the next that came is the complete binary tree concept. The concept that came is the complete binary tree. Now, what is the concept of the complete binary tree? That if you represent a binary tree in an array, then there should not be empty location or gaps between the elements. That means from first element to the last element, first element to the last element, there shouldn't be any gap present in the array. And if the gap present in the after the last element, then there is no problem. Then there is no problem. That means if we want to check here, if we want to check this, then A, B, C, D, E, F, G. So no gap is present. That means it is correct. It is a full binary tree as well as the complete binary tree. Because complete binary tree states what? Complete binary tree states that there shouldn't be any gap present between first element to the last element. But after last element, there may be gap present. There is no problem. But between the first and last element, there shouldn't be any gap present in the array. So this, if we take this our tree, then this tree is full binary tree as well as complete binary tree. But if we want to see this, here you see, if we want to check this, in this, it is not the full binary tree. It is not the full binary tree, because if to make this as a full binary tree, we have to add two elements. Then if we add two elements, then this tree will become the full binary tree. So that means this tree is not full binary tree, but this tree is the complete binary tree. Because what? Here the gaps are present. The gaps are present after the last element. So if that means A, after that B, C, then D, E, and after that the gaps are present. So that means this array, if we take this tree, then this tree is not full binary tree, but this tree is the complete binary tree. This tree is the complete binary tree. But if we want to check this tree, then this tree is not applicable for the full binary tree as well as the complete binary tree. This tree is not the full binary tree as well as not the complete binary tree, because there is, if we want to make it full binary tree, then we have to add two elements here, then only it can become full binary tree. And also the gaps are present between them. You see the gaps are present between them. So that means this is not the complete binary tree also. So this is the concept of the complete binary tree and the full binary tree. Okay. Clear?
Yes, sir.
Till now it is clear?
Yes, sir.
Okay. So the height of the complete binary tree, the height of the complete binary tree will be minimum. Only that is the log n. And the height of a complete binary tree will always be log n, because unnecessary, we are not going to the next level. Unnecessary, we will not going to the next level unless one of the level is filled. So the height of the complete binary tree, height will become minimum, and minimum only that is log n. And the height of the complete binary tree, height of the complete binary tree will always be log n, because we are not going to the next level. We are not going to the next level unless the level is filled. So this is the concept of our complete binary tree and full binary tree. So after completing this, we will now move into the max heap concept. So the max heap and min heap, this concept we will now move into it. So the max heap is what? In the root element for max heap, the element that is present in the root must have the highest value, and its children will contain lowest value. Now, if you see this, that the maximum number here is in the root. If you check through all this graph, is not sorry, if we check all this tree, if we check all the tree, then you will see the maximum number element is present in the root. You see here there is 50, 30, 20, 15, 10, 8, 16. So between them 50 is the maximum. That's why it is present in the root here. Maxive concept is that the parent will contain maximum value, and the descendant or the child will contain the lowest value. So here the maximum 50, and its left child it has 30 value, and the right child it has 20 value. That means between them 50 is the maximum. So 50 becomes in the root. Then for 30, there is a left child that is 15 and the right child value is 10. So between them, 30 is the maximum. So 30 is present in the root. Same as that for here also, there is 20 and in the left child it is 8 and the right child it is 16. So between them, 20 is the maximum. So that's why 20 is present in the root. So maximum value for case of maxive, maximum value will be present in the root and its child will contain the lowest child will contain the low value. In the mean heap, the concept is just the opposite. The concept is just the opposite. Here, the root will contain the minimum value. In mean heap, the root will contain the minimum value, and the child then or the children will contain the maximum value. So that's why you see in the root, if you follow through this tree, then 10 is the minimum value. So that's why this 10 is in the root. That is 10 is present in the root. And here next there is a child that is present. For left child it is 30 and right child the value is 20. So after that for 30s left child is 35 and for 30 the right child is 40. So that means between them 30 is smallest. So 30 is smallest, that's why 30 is present root. Same as that for in this case also the left child is 32 and the right child is 25. So between them 20 is the minimum. So 20 is present in the root. So maxive concept, maximum value in the root, and mean heap concept is minimum value in the root. Now if we represent it into an array, if we represented it into the array, then it will looks like this. It will looks like this, that here it will be 50 first, level by level we will fill up. We are not using the formula now, we are using by level, we fill up the value in the array. So first 50, after that it will be 30, then 20, then 15, then 10, then 8, then 60. Same as that for mean heap concept also, if we have to put the value in the from mean heap to the array, then also the value will be present like that. That first there will be 10. First the value will be 10. After that it is 30, then 20. After that it is 35, then 40. After that the 32 and then 35. So this is the concept that we can fill the value in the array. Now we will see the first operation. The first operation that is we perform in the maxive. Then how we perform the first operation. That is the insert operation in the maxive. The insert operation that we can done in the maxive. So how the insert operation is done. Now let's say an element is given 60. Now let's say an element is given that is 60. So we are taking this concept. Let's say an element is given as the. Now for in this maxive, I have to add this 60 element. Now where I should add this 60 element? You and everyone like this will say that 60 is maximum value. So that means we will put 60 here. We'll put 60 here, and after this put 60, like this, we will show that a tree will be shown, and in this there will be, in the right child there is no tree present. So like this we will put, but this is not the concept. That means everyone will say because maximum value will present in the root. That means we can place 60 here, we can place 60 here, and age we will give like this, and in the right there is nothing. Like this we will present the tree, but this is not the concept. So what is the concept, that how we can insert it? So first we will insert it into here in this left. We will put whatever the value is, we will first put it here. Now you can ask question that why here also we can put, 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 here also we can put. But I have not choose any of the places here. I have only choose this left side place. Now, why I have chosen this left side place? There is also a cause. Now, what is the cause? The cause is, if I choose, let's say, if I choose 60 here, if I want to place 60 here, then if we represented it into an array, the gaps will gain, because here there will be gap, and here it will be gap, then here it will be gap, and after that the value came, and after that there is the gap will be present. So that means this tree will become not a complete binary tree. We want the tree that is present, that tree should be present, because if we place this 60 here, then it will break or violate the complete binary tree concept, or the complete binary tree concept rules. It will be violated this, because the gaps will came, and if between the first element and last element the gaps came in between them, that means that tree cannot be, the complete binary tree. But if we place 60 here, if we place 60 here, that means 60 will came after that. In the 8th position, the 60 will came. So there will be no gap present. There will be no gap present. So that means this is not violating the complete binary tree concept. Okay, so it is not violating the binary tree concept. We can place 60 here, but this is violating the max heap concept, because max heap is doing what? Max heap saying that the root value should be maximum. The value that is present in the root should be maximum. That means here 60, but here in the root the value is 15. It is violating the root. So what we will do now, we will compare it first. In the first step, we will compare it with this root. Now between them, 60 is the maximum. So 60 will be swapped here, 15 will go here. The next step, here 60 comes, but here also in the root 30 is present, but here this is 60. So that means we require swapping. So again, the 60 will move here and this 30 will came here. Then again, we will check, but here also the root value is less. So that means we have to 60 move here now. So we have to move the 60 here now. We have to move the 60 here now, and this will be moved here. This will be moved here. 1 minute. 1 minute, please stop. I will start the class. Is 2020 pass out. 2020 pass out. कौन सा सीसी का सीसी का इस स्लाइड में देखो, इस स्लाइड में कोई है? इस स्लाइड में इधर से तो cycle cycle okay, so then 60 will move here and 60 will move here and 50 will move here. So it will looks like this. It will looks, you see, the tree will now looks like this. So that's how the value should be inserted, and we should check these properties. These properties we have to check. Okay, समझ में आया? समझ में आया कि कैसे वैल्यू इनपुट करना है मुझे मैथ सीट में? एनीवन, कोई क्वेश्चंस है?
No, sir.
आदित्य, अभी सबको और कोई अपेक्षा?
No, sir.
Okay. Oh. So that's how the value should be inserted. So from here, we can say the time taken for insertion, the maximum time can be of order log n, we can say the maximum time it will take order of log n, because if the height of the complete binary tree will be minimum, only that is the log n. So the height of the complete binary tree will always be log n. So in this case, how many comparison we have done? 1 comparison, 2 comparison, 3 comparison. So if the order is n, then log n comparison. So there is 3. Height of this is what? The height of this tree is 3. So that height of this 3, and we did that 3 comparisons. So that's why we are saying that if the maximum time will take, that means if the height of the tree is log n, here we are in this, if in this example we see this is 0, this is 1, this is 2, and this is 3. So that means the height of the tree is 3. This height of the tree is 3, and we require 3 comparison. Then in the complete binary tree, this is also a complete binary tree. If this is the complete binary tree, then that means the height will be log n. So the height will be log n, and maximum comparisons it required log n comparison. So it will be order of log n. And the minimum will be what? If let's say in this case the value it is given 60, and if there the value, let's say it gives let's say 9, or not 9, let's say only 5, it is given the value we have to insert is 5, then that means we can add 5 directly here. We do not have to require comparisons, or do not have to require to swapping the values, because 5 is less. So we do not require, because in root there is already the maximum value is present. So no comparison is needed. Here no comparison is needed. So that means a constant time is needed. So here it will be order of 1. The minimum time, because there is no comparison needed, so that means it will require constant time. So we represent it as order of 1. So minimum time will be order of 1, and the maximum time will be order of log n. Okay, so this is the insert operation in the math sheet. Clear? Siaram, Pooja, सबको समझ में आया? Okay, so in the next class, we will continue this, the deletion of the in the max heap, then in the main heap also we will see the insertions and deletion. And after that, we'll move to the heapify concept, heapify and the priority queues, we will move there. So today, this much, we'll continue in the next class. So thank you, everyone.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Okay.